Hello students, today we'll be going through the TOV equation. So this is the solution of the Einstein equation with matter content. Okay, uh, like we have done earlier, let us demand that we demand for a static and spherically symmetric solutions. So that let us say that this is a solution for a star, okay, which has matter in it, and the star is static and spherically symmetric. So the metric is, or the geometrical part is given by this line element, uh, u r dt square plus v of r dr square plus r square d omega square. This is a very general line element for a spherically symmetric solution, and as I have told you, it can be written in the form of, in terms of exponential, e to the minus 2 nu, there will be dt square, sorry about that, it was 2 lambda dr square plus r square d omega square. Okay, so there will be dt square and dr square here, sorry about that. So now once we have written this line element, and these are the coefficients of the temporal and the spatial coefficients, I can write down my metric, and it is of this form. The inverse metric is also very easy to write. It is only inverse of as this is a diagonal metric, all elements are the inverse of these elements. Okay, once we have done that, so now is by our formula of finding the Christopher symbol in terms of metric coefficients, I can find all the non-zero metric coefficient for this metric, and this 1 means r, 0 means t. So r tt coefficient is nu dash exponential 2 nu minus lambda. This t rt is nu dash, and gamma t tt equal to lambda dash. So we can also have the gamma t gamma r theta theta component, gamma r phi phi component, and gamma phi theta phi component. Also these are the non-zero components. Also gamma theta r theta component is equal to gamma phi r phi component, which is 1 by r, and gamma theta phi phi component is minus of sine theta cos theta. So this you can find easily. So once you have done that, you have found the Christopher symbols, then we can find the Ricci tensor, okay, in terms of the Christopher symbols, which is also very trivial for you, and it comes to be of this form: r00, or that means the tt term is nu double dash minus lambda dash nu dash plus nu dash square plus nu dash by r. It was twice nu minus lambda. R11 is minus nu double dash plus lambda dash nu dash minus of nu dash square plus 2 lambda dash by r. The Ricci coefficient, the Ricci tensor of theta theta is minus of r nu dash plus r lambda dash plus it was twice lambda minus 1 whole to the multiplied by exponential to the power minus lambda, and r phi phi is nothing but r22 multiplied by sine square theta. So we have got the Ricci tensor. We can also, if we find the Ricci scalar, we can also find the Ricci scalar by this formula, and which is given by this big coefficient, or this big equation. Okay, it has all nu dash lambda dash r square nu double dash, okay, lambda dash, and the exponential of twice lambda. So this is all the part of the geometrical part. Okay, so however, as we have told you, this is not a vacuum solution, this is a solution with matter, so we need an energy momentum tensor. So before that, usually it is useful or more convenient to work in the mixed representation. If we are writing the solution of, if you want to write the solution of this matter Einstein equation with matter. So for the simplest one, we just take the matter to be of perfect fluid, where this T mu nu is given by epsilon plus P. Epsilon is the energy density, P is the pressure, U mu is the force velocity, U mu nu plus P G mu nu. So this you have encountered earlier when we have discussed the energy momentum tensor for a perfect fluid. So now we have the geometrical part, we have the perfect fluid part. So what we can do is we can uh, so I can also write this G mu nu, that is the Einstein mm, this total geometrical part, which is nothing but r mu nu minus of half r. So I can write that. So gtt becomes exponential to the power minus twice lambda 1 by r square minus 2 lambda dash by r minus of 1 by r square. This can be written in terms of a total derivative of minus d by dr of r 1 minus exponential twice lambda by r square. Okay, also you can write grr, pardon me about mixing my notations t and r. Some before I have written in terms of say 0 and 1, but remember the t is equivalent to 0, r is equal to 1, theta is equal to 2, and phi is equal to 3. So once we have done that, we can write all the other also, we can all the other geometrical part for the Einstein tensor. Okay, so next, if once we have written down all these equations, next we will also assume that as we have assumed that we have a static star, that means we have del dr by del tau is d theta by del d tau, and d phi by del tau equals 0, and dt by d tau is equal to exponential of minus nu, which gives, this is the 4 velocity, right? Only the 4 velocity u0 is non-zero. That means only the temporal part of the 4 velocity is non-zero. Once we have written down that, we can find out the Einstein the energy momentum tensor temporal and the spatial part. This will again be a diagonal metric where the temporal part is equivalent to this minus of energy, and this and the spatial parts are all equivalent to pressure. So this we can also check with this 4 velocity formulations, right? U mu equal to -1, and if I for a static star, and then so if I assume it to be in the equatorial plane and it's static, then I get this equation. And for a static star, I also have this ui to be 0, only this remains, which gives me u to be ut to be equal to e to the minus. This is nothing but this. Okay, this is written in terms of the 4 velocities. Okay, so once we know the 4 velocities, you can easily plug it in here and find out. And we know g mu nu, you also know u mu u nu, so you can find out every element of d mu nu, which is a diagonal metric, and we have found out that to be equivalent to minus energy, the temporal part, and the spatial parts are all equivalent to the pressure. Okay, so we have everything we need to solve the Einstein equation. So writing the Einstein equation and equating terms by terms. Okay, so we can do that, equating term by term. This is, remember this equation 1, or what we have given, this is we have done, this is written as this equation. Okay, this equation, we take this equation and we write the Einstein equation, full Einstein equation, equating this geometrical part and the matter part. So we know we can write down that d by dt of r 1 minus e to the minus twice lambda is nothing but equal to 8 pi epsilon. 8 pi comes from the Newtonian equivalence, which we have found out from the social metric. Okay, this k terms is equivalent to 8 pi. There is also g, but we have assumed g to be 1. Remember that g and c are assumed to be 1 here. Okay, so this equation can easily be integrated. You can do that, and you will you can find that e to the minus twice lambda is nothing but 1 minus 8 pi by r integration 0 to r epsilon r square dr. Now we define a quantity which is known as let us say that for the time being mr. Okay, this is the mass, you know, this is the mass, and which is defined as 4 pi 0 to r epsilon r square dr. This is the energy density or the mass density, anything we can want to call it. So if I define this quantity to be this, then this equation becomes e to the minus twice lambda equal to 1 minus 2m by r. Okay, so we know how lambda varies with r. Okay, so this is the first equation. Let us call it equation 1b. So the next equation, the other Einstein equation, this equation we got from the first equation, remember, and the other equation, this is from this equation exactly. this from this equation. Okay, so this we get from this equation. So other equation, the GRR equal to 8 pi p. This is, gives the relation of this form. Okay, exponential to y, exponential minus of twice lambda 1 by r square and nu dash. Okay, G theta gives this form, and G phi phi, as you know, is equivalent to GT regular GTT G theta theta, because in both sides we have sin square theta, which gets cancelled. Okay, so this is the things we need to solve. Okay, so how to go about solving this equation? Okay, so let us this equation is multiplied by r square and brought in the form of equation 1a. Okay, this equation. Okay, this means this equation which you have solved for e to the minus twice lambda. Okay, so for other to find the other unknowns, which are this mu. Okay, and let us say that how this pressure evolves, all these things we have to do some more work. Okay, so what we do is we add equation 1 and equation 2, and adding them gives gives this equation 8 pi epsilon plus p equal to twice by r e to the minus twice lambda lambda dash plus mu dash. So lambda dash can be eliminated with the help of equation 1b. So differentiating equation 1b with respect to r, we have this. Okay, this equation, and if I substitute this in equation 5, and after a bit of algebra, this is not much, you will get this relation. Okay, so once we get this relation, that means I can solve for nu dash. How nu dash means dash here means derivative with respect to r. Yeah, so remember that derivative with respect to r, because everything is in terms of every coefficient varies in with r. It's a function of r. Okay, so nu dash means derivative with respect to r. So nu dash, how nu dash changes with r is given by this formula, which is 4 pi r cube p, the pressure, plus m, the mass we have defined, by r square 1 minus twice m by r. Okay, this is the coefficient you remember. Okay, from the stoichiometry. Okay, this also comes here again. Good. So we have found out how this lambda and nu varies with r. So what about other things? How the pressure changes? Okay, so we can also calculate that from equation 1. From equation 1, so we have mentioned equation 1 here. Okay, let me see, this is equation 1. Okay, from equation 1, what we can do is we can we can solve, we can again solve it to have this. Okay, and equation 2 can be written again in terms of this. Okay, this is given in terms of lambda dash, and equation 2, from equation 2 we get equation let us say 8 in terms of nu dash. Okay, so differentiating equation 8 with respect to r. Okay, this equation with respect to r, this is very simple, you can do it. We get this big expression. Okay, and multiply both sides by r, and then solving for nu dash, nu double dash, we get nu double dash to be this whole big expression by twice of r square. Okay, and we can also solve for nu dash, okay, from this equation, or you can use the nu dash we have got there. So also we remember that our g theta theta was equivalent to this exponential to the power minus twice lambda nu double dash plus nu dash plus this. So we know we know what is nu double dash, we know what is nu dash, we know what is lambda dash. So I can plug those things here and solve this equation. You remember there will be term in terms of p and p dash. So we will be solving for p dash. P dash means dp by dr, how p changes with radius. Okay, so I can do that everything here, and I will come up with this equation, twice of r dp by dr gives me p plus epsilon 1 minus r minus twice m of r 1 plus 8 pi r square p. Okay, so I can solve for dp by dr, which is given by p plus epsilon m of r plus 4 pi r cube p of r and r minus twice m. Okay, and these are the other two equations that we have derived. The whole three equations gives us how the pressure changes along the radius, okay, of a star, how this mu changes, nu changes with r along the radius, of the star, and how lambda changes along the radius of the star. So these three equations, along with this equation for the mass, this is how mass changes. This equation gives us 1 minute. Where is that? Yeah, this equation gives us how the mass changes along the radius, or how mass is accumulated as we go on solving as the star grows. Okay, so this gives the equation for the mass. So along with this three equation, the mass equation gives me the what is known as the Tollmann-Oppenheimer-Volkoff equation, or TOV equation. This represents the solution of a Einstein equation for the interior of a spherically symmetric star, relativistic star, definitely. Okay, so this is a very interesting result which was solved by Tollmann-Oppenheimer-Volkoff, which gives the how the pressure and the potentials and the relativistic potentials, gravitational potential changes across the R. Okay, so we cannot solve this four equation directly. To solve this four equation, you need a relation between epsilon and p, because here you remember there are p and also epsilon. So we need a relation between p and epsilon, which is given by the equation of state. Okay, equation of state is gives merely the relation between epsilon and r, or the energy density as a function of pressure. And now if I, along with this equation and among the four equation, I can I can solve for the how the star, solution for the relativistic star. Okay, and observe that the mass relation is a non-relativistic one here, which is the gravitational mass, the mass in the gravitational field. However, this is not the proper mass. Proper mass has some gravitational correction along with it. You can try to find that out. So how can we solve this equation? Okay, so what we use to solve this equations are useful mainly in solving what is known as the neutron stars or the pulsars. Okay, so this is also a rich field that has evolved with time, and in the recent years that have got a very prominent exposure due to the finding of the radiation wave from binary mergers. Okay, so what are neutron stars? Neutron stars are rotating, highly condensed rotating stars, which gives off say radio waves, pulses along their axis of rotation or along their magnetic poles. Okay, so how to solve for these stars? How to obtain these stars with these equations that I have told you, with the TOV equations? Okay, so what we do is we start with some central density. Okay, let us say that we have a star which central density, we have a star, let us say that which has a central density of this. So if I know the equation of state, we have a particular equation of state if I take. Okay, and then equation of state will give me what is for that particular density, what will be the pressure. Okay, so then I start solving these three equations. Okay, so as I solve, as r, we start with very small r is not equal to 0 because 0 has some problem, so very small r, and then we integrate all these four equations, the pressure equations, the nu equations, and the lambda equation, and the mass equation. So you see that the pressure equation, it is negative. Okay, so at the center the pressure is maximum, and as we go out we solve it by increasing small r dr. For every dr we solve it and we integrate it. Okay, we solve this differential equations, and for every r we get a less and lesser p. Okay, and then we find, and this pressure decreases, however the mass increases, because mass is accumulation of the mass that we are doing in the integration. So, and then we stop. When do we stop our integration? We stop at the surface of the star. How do we define a surface of the star? The surface of the star is defined when the pressure is 0. So we start with some pressure, or we start with some energy density and found the corresponding pressure, and then I solve this equation to find the pressure at the next outer point. Okay, and as I go out and out, this pressure decreases, and ultimately it goes to 0 at the surface, and the surface is defined at the point where pressure goes to 0, and the total mass of the star is defined at the mass accumulated at the till up the surface of the star. So so we get a solution for a star. We get how the nu and lambda varies across the star, what is the radius of the star, what is the mass of the star, and all those other things. Okay, so starting with a certain central density, we have obtained a mass. We can start with another central density, and we will end up with another radius and another mass. So for a particular equation of state, we generate a called a sequence of stars, which has a particular behavior. Okay, so this sequence of stars for a particular equation of state gives us the what will for different densities, what will be the mass and the radius of the star. Okay, so this is how we solve the TOV equation for relativistic stars. Right. So you can also you can also go to the non-relativistic limit. So your another homework is finding what is the non-relativistic limit of this equation and what are the relativistic and GR corrections of this equation. You can try that. So thank you. Hello students, welcome back for the next topic of today's lecture. So some other standard black hole solutions. So we have till now we have seen the standard solution of a black hole, which is given by the Schwarzschild metric. Okay, and which is a static symmetric in free space solution of an Einstein equation. So here and again we have in today's first lecture we have seen what is the static spherical symmetric solution of Einstein equation with in presence of matter. Okay, that gives us the solution of say relativistic stars. Okay, next what remains is what are the other black hole solutions we can encounter. There are numerous black hole solutions at present going in the literature. So I will discuss the two most important black hole solutions. Okay, and here what the strategy I will take is I will do some mathematics, but not the every detail of the mathematics will be done here. You can do that if you are interested. You have to go take some advanced book which deals with this type of mathematics of black holes, some non-trivial black holes, and you can do that. But I will not go into the whole standard solution of this standard black hole solutions, how means derivation and all those things. So the first black hole that we can think of is a charged black hole. So if charge is present, T mu is not equal to 0. So previously we had T mu for a relativistic star, okay, where T mu was also not equal to 0, but for that we had a matter. The non-zero term of the T mu was coming from the matter. But here the non-zero term of this T mu will be given by the charge of the black hole. So we can throw some charge in a Schwarzschild metric and see how the black hole behaves. However, the total charge Q is very less than the total mass of the star, gravitational mass of the star. Okay, so otherwise it will lead to some instability, and you can read about that. This is very complex calculation. We will not do here, but usually this is the case. The charge of a black hole is much lesser than the gravitational mass of the star. Okay, here we demand that the star is still static and spherically symmetric. It is non-rotating and spherically symmetric. Therefore, it is spherically symmetric. So our old line element still holds. Okay, this is the old line element that we have solved for this non-relativistic stars and even for the Schwarzschild metric. Okay, this line element still holds because we are still in the static and spherically symmetric condition. Okay. However, now the field due to charge particle has changed the energy momentum result. So what can we think of this charge particle? So we have a charge particle which is at the origin of the coordinate and which gives rise to the electrostatic field. So now this field due to this charge at the origin of the coordinate, let us assume to be purely radial. Assuming that there is no magnetic pole. If there are magnetic monopoles, there will be a bit more complication, but it's not hard to calculate. But we will not do that. We are assuming that there is no magnetic monopoles. Okay, we don't know whether there are magnetic monopoles or not. Magnetic monopole has not still been discovered, so people assume that they are not present. But theoretically there is no restriction on not having magnetic monopoles. However, for our case, to make our life simple, we assume that there is no magnetic monopole. You can also solve this case perfectly for assuming magnetic monopoles. It will not change much. The result will not change a bit. Okay, you will have to do with a bit more mathematics and careful analysis of that. So let us skip that and say that we have only a electrostatic field which is a purely radical. Okay, if that is the case, then this our Maxwell stress and Maxwell tensor is uh, is given by this E radial, the electroradial, and this metric is only this TR and RT are non-zero, and all other metric coefficients are 0. Okay, so if I have written down this Maxwell stress energy tensor, then I can also solve the Maxwell equation. This you remember I have got this two Maxwell equation from the when I was discussing energy momentum tensor explicitly in our class during this before the mid-sem break. Okay, so these are the two equations. Okay, this is the covariant derivative, and this is the stress and tensor or this field. Okay, and these are the two equations that they respect. Okay, equation 3 is automatically satisfied by this metric and the line element, so there is we do not get any new equation. However, equation 4, if I plug in it here, it gives me this relation: exponential to the power minus half alpha plus beta r square e to the power whole derivative is equal to 0, which gives us that e is exponential half alpha plus beta by r square epsilon. Epsilon is the integration constant. However, we know that for r tending to infinity, this line element should represent the Minkowski metric. Okay, flat, asymptotically flat, right? So alpha and beta should be 0 there. So at e tending to r at large distance from this black hole or from this metric, we will have asymptotically flat region where the electric field is given by this will be 1, so epsilon by r square. So epsilon, we can from this we know that this is nothing but this charge from our known knowledge of this electrostatic field given by epsilon is given by is known as the charge. So this is nothing but the charge of the black hole. Okay, the charge we have thrown into it to along with the Schwarzschild metric. Okay. Then next thing is solving the Einstein equation. So again, you can you have this metric. Okay, you have this metric. You have this metric, right? You have ER epsilon ER. You know how it behaves. Okay, so you have this metric. You can calculate this for the geometric part. You can calculate the Christopher symbols, the Einstein tensor, the Einstein Christopher symbol, then which is tensor, which is scalar, and from there you can find out the Einstein tensor G mu nu. Okay, and from the matter part you can also find out this T mu nu. Okay, so once you get that, you then again solve term by term, and you can do that very easily. I will not go into that. If you are interested, you can do that, and if you will get a solution of this metric, which is known as Reisner-Nordstrom metric. Okay, and that is given by d square equal to delta dt square plus delta inverse dr square plus r square d omega square, where delta is nothing but 1 minus 2m by r plus q square by r square. Q square is the, sorry, this is q is the charge. Okay, this q is this epsilon, I think. Yeah, this is q is this epsilon. Sorry about that, change it coefficients. But this is equal to epsilon equal to q. Just remember that. Okay, so this is this metric equation that is sitting here. It depends on this, the mass, the so-called mass of the black hole, this radius, and the charge. So now, as we have done for the Schwarzschild metric, you can calculate this invariant curvature, invariant this invariant form of this. To find the curvature similarity, you can calculate this invariant scalar, which is given by this, and you will see that if you put you get some equation here, and if you put r equal to 0, it will blow up. So r equal to 0 is the curvature singularity. However, there is also a coordinate singularity. You can see that this, if delta goes to 0, this it goes to this thing blows up. Okay, and however, this delta is not r equal to 0. It is not the curvature singularity. Okay, this is the coordinate singularity. It can be avoided. Okay, so delta is 0 when, if I put this to be 0, so I will get some relation with the r, and r has, this is r squared term, so we have both positive and negative solution, r plus minus, which is given by m plus minus of root over minus square plus q square. So this, we have two radius in which this goes to 0, delta goes to 0. Okay, this is a new thing that we encounter. We had not encountered this before, because in Schwarzschild metric we saw that r was the coordinate singularity is a single point, which is equal to twice m or 2gm, if we want to recollect this gravitational constant. Okay, so but here we have at 2 points we have this there is a singularity, this things blows up, and this is something new which is coming due to the throwing of the charge at the black hole. So for a charged black hole, so there can be 3 cases, right? Because this is a quadratic equation, we can have 3 cases. The first case is, let us take that m square is less than q square. Okay, since we are assumed m to be very greater than q, and m square is less than q square, so this is a negative term. However, this is so this will decrease that, but m will remain positive, so delta is always greater than 0. So what will happen to this? So this m square is less than q square, this is less than this. Okay, so this will always remain positive. Okay, so if delta is always greater than 0, so the metric is regular till r equal to 0. So till the curvature singularity, the metric is regular. Okay, that means we don't have any coordinate singularity. So you see that then this t coordinate is always time-like and r is always space-like. It doesn't flip over, that as we have seen for the Schwarzschild case, at this event horizon or at the event horizon, they flip, right? R becomes time-like and t becomes space-like. However, there is no regions of such in this, for this first case, and t always continues to be time-like and r always continues to be space-like. So there is no event horizon. Observer can go to the singularity and come back. Okay, because r is always space-like, right? We can go and we can always stop. There is no time-like line which we have to follow always. If there is you remember that if there is a time-like line, we have to always follow that line, because time-like means we are going towards positive t, right? And we always have to follow that line. However, for the spatial coordinates, we don't need to do that. We can go any direction. So observer can go to the singularity and come back. So there is no way we can come back from the black hole. So we can go and find and see the naked singularity there and observe it, and then come back to report our result. And then the singularity, which is the curvature singularity r equal to 0, is known as the naked singularity. So if you calculate the geodesic, you will find the singularity is repulsive. Okay, so you can find that it blows up as r goes to 0. So the time-like geodesic never intersect r equal to 0. Okay, so it never goes to r equal to 0. Null can reach r equal to 0, but in some special cases we will not talk about that. Okay, no naked. However, this naked singularity is still not had been noticed, and there are many studies which conclude that they are unphysical. Okay, that studies will not go into, but this is not conclusive. There are also studies which shows that they may not be they may be physical, but we have not seen them. So there is a dispute about that, but we will not go too much further. If you're interested, we can look into that. What are naked singularities? Okay. Next case is when m squared is greater than q squared. That is the interesting case. Okay. So this is the case which I have talked about. M squared is less than q squared. So a particle approaches here. Okay. it bends somewhere here, but it never. This is a repulsive. This it reaches, but it very slowly. Okay, it reaches r equal to this r equal to 0 at very small case. This delta becomes. Okay, so this is the case we have discussed. So next case will be m square greater than q square. Okay, so delta is, so we have delta r greater than 0 for a very large and small r. So you can, for m square greater than q square, you can find what will be this. Okay, so this is m square is greater than square, so this is m is something which has two values, r positive and r negative. Okay, and if you put it back here, you will find that delta is greater than 0 for very large and very small r. That means between r plus and r minus, this is greater than 0. However, between r plus and r minus, it is less than 0. So this thing's getting interesting here. So we have coordinate singularity at r plus and r minus. So, and this could be removed. Once it is a coordinate singularity, this could be removed. So this r plus and r minus are the null surfaces. You can check that. Okay, solving the null geodesic. So these are the event horizon, and r equal to 0 is a singularity, which is a time-like. Okay, so this is interesting. The r equal to 0 is a time-like singularity. Okay, and r equal to r plus minus is a null surfaces. It's a event horizon. So what we do is, let us assume that we are approaching this black hole from a very far away. Look at this charged black hole, this Reisner Nordstrom black hole from very far away. So very large r from, let us say that this is the path of for this case 2. So we are approaching here. Okay, first we encounter is r plus, radius where r switches from space-like to time-like. Okay, so once we have reached here, there is no way to go. We always have to follow this line. Okay, because this is the time-like line, right? R switches from space-like to time-like, so we have to follow that. So we have to follow the fall. No other way to escape us. So we fall down for now till r minus. Okay, and fall last is r minus. After r minus, radius here again is become space-like. Now we get the interesting part. So here motion may be arrested, right? Because we are going towards decreasing r, but r is space-like, so we can go towards decreasing r, or we can come back to increasing r. So it is not necessarily that we go and hit the singularity. Okay, we go and to r equal to 0, proceeding from we can stop here. We can again come back. Okay, so we can do the both. We can, if I go proceed from here, we can see the r equal to 0 and then come back. We can I can also do that. We can go and see the naked singularity. I can again come back, and while come back, when we can move backward from r equal to r minus. Once we reach r minus, okay, so when we are coming back, once we reach r minus, then this line is the time-like line. This is the time-like line, and this is the direction of the time-like. So we have to, from once we reach r, if I starting from here and coming like this, once we have reached r minus, we have to go to r plus. There is no other way. That is the time-like direction. Okay, so we have to go and r plus. So we can come out of r plus, right? And one at r plus, we are again, that is on space, this radial direction is the space-like. So we can proceed like this, we can proceed like this, and come back to from where we have originated and report our findings, or we can again go back. Okay, so we can do that, go back to r plus, r minus, and then r equal to 0, and again come back. We can continuously do this type of play. We can go back here, again come back, and again we don't go, and again we can come back. We can go this as many times as we like. Yeah, but it will depend on this mass of the black hole, the charge, and your lifetime, and your body to adapt to the tidal forces. So we can go back at large and share our experience. Can also again move to r plus and inside a black hole. Can repeat the process any number of times. So if I do this, what will be the Penrose diagram? Okay, the Penrose diagram is very interesting. See, r equal to 0 is a time-like line. Okay, this is not a point, is a line, r equal to 0. Okay, so, and this is I plus, these two are r is equal to 0. This is I0, this is I0, this is two-dimensional suppressed. Okay, this is I minus, this is I minus. So time-like things always start from here and goes towards here, right? And I can do that many times, right? I can go back, always go back. So let us plot this, show it for many such say uh, diagrams. Let us connect these two diagrams. So what we can do is, we are the time-like trajectory, right? We are massive particles, so we have time. So we can start from here, like we can start even for I minus and go towards I plus. Okay, so we can start from here. We can cross this R plus. This is the R plus line. Once we have R plus line, we have to go to the R minus. Once we go to R minus, we can go to the naked singularity. Not the naked singularity, R equal to 0. Here there is no naked singularity, R equal to 0. However, we can also start here. We have to, once we cross R plus, we have to go to R minus. But from R minus, we can again come back to R plus and then come back again to other to this new world. Okay, new world which we see. We can continue this again. We can follow this here, and again we can do this continuously. So this Penrose diagram is very interesting for this charged black hole. Okay, you can think of many other interesting phenomena here. So the last thing that I want to discuss is what happened with m square equal to q square. Okay, this is this in this diagram. This is this path. Okay, this is this path. Okay, so here if m square equals square, we only have a one solution. Okay, remember the delta equal to 0 at r equal to m, which is the event horizon. Okay, r equal to null at r equal to m, and the space like on either side. So this is r equal to the radial coordinate is space like on other side. So we can arrest our fall. We can always choose going in this direction, but only one thing is restricted. Try to plot this diagram. Okay, you can avoid the singularity. That is the case. We can avoid the singularity. R equal to 0 is time like. Okay, and either side of the r equal to m is null, and on the other side the radial coordinates are space like. So we can always avoid the singularity and proceed. Okay, so this is the interesting case of charged black hole, Reisner Nordstrom black hole. So next, what we'll discuss in the next is let us now start a rotating black hole. This is the most interesting and the most physical black hole that has been observed in the universe. Most of the black holes that has been observed are rotating black holes. So this is the most physical black holes that you can encounter with. Okay, however, once it is rotating, so this is no longer a spherical symmetry. Okay, so it is not a static solution. So, and also the spherical symmetry is not there, so it is difficult to solve. The Schwarzschild metric, the Tollmann-Oppenheimer-Volkoff, and the Reisner Nordstrom metric was solved after the Einstein equation was written down within I think maybe maybe a decade or 15 years. However, a lot of time was taken to solve the equation for a rotating black hole, Einstein equation for a rotating black hole. So what we demand here is we have two demands, that the black hole is, or the metric is actually symmetric. So around an axis of rotation, let us say that theta equal to 0, that maybe that axis. Okay, around that axis of rotation, which is actually symmetric, and is stationary. Stationary means there exists a time-like killing vector. So it is actually symmetric and stationary. These are the two demands that we make. Also, we will not demand to be static and spherical symmetry. So this this derivation is very complicated. So I will not go into that. So this solution of the Einstein equation with this with these conditions was first done by Kerr. Okay, and the metric, the line element that he came up with, which satisfy all these conditions and the Einstein equation, is this, which is minus of dt square plus rho square by delta dr square plus rho square d theta square plus r square plus a square sine square theta d phi square plus 2m of r by rho square a sine square theta d phi minus dt. Okay, so this is the Kerr metric. Okay, this is the Kerr matrix, and this is in the Boyer-Lindquist coordinate. This is the most famous and most studied coordinate in which the Kerr metric is studied. It is also written, the Kerr himself wrote this metric in, I think, in Cartesian coordinates. However, that is not useful now. The most used one is this. Okay, this Boyer-Lindquist coordinate. Okay, and remember there are many interesting things going on here. Okay, so see, this theta is, this angular part are no longer can be written in terms of a conformal factor outside. Okay, the theta and phi are different, had different coefficient in front of them. Not only sine, different not only by sine square but many other things. Also, there is a cross term of phi and t. That means it is rotating around along theta equal to 0 axis. That means along this phi. So, and once this is the case, once for every axially symmetric thing, this is this term is a, this cross term of phi and t is a new thing, and it will always come for any rotating solution. Remember that any rotating solution will have axially symmetric rotating condition, will have this cross term of phi and t. So these are the many new things have crept up in this metric, and we should look into them one by one. One is this cross terms that I'm talking about, which is always be there. Okay, so what is so first we define what is delta and what is rho square. Delta is defined as r square minus twice of mr plus a square. Okay, and rho square is r square plus a square cos square theta. Okay, you can identify that a with the rotation of the spin of the star. So if we put a equal to 0, so this delta is r square minus twice, so this is r square, means r square plus a square, so this goes to 1. Okay, and a tending to 0 will give back oh no, this is r square by r square minus twice mr, so that this will give me 1 minus 2m by r coefficient here. Okay, so this gives us the a tending to 0 gives us the Schwarzschild metric, a equal to 0 gives us the Schwarzschild metric. If I keep this a to be fixed and m, what is m is this, m to be 0, then what we'll get is, we'll get the line element of this form is d square equal to minus dt square plus rho square r square, rho square by r square plus a square dr square plus rho square d theta square plus r square plus a square sin square theta d phi square. You can see, you can identify this with the ellipsoidal, and this is the flat space in ellipsoidal coordinates. Okay, so keeping a fixed and tending m to 0 doesn't give back our Schwarzschild metric outside, so it gives something of ellipsoidal space time. Okay, so we can also go back from this coordinate to the Cartesian coordinate with the identification that x equal to root over r square plus a square sin theta cos phi, y equal to root over r square plus a square sin theta sin phi, and z equal to cos theta. We can write the metric in terms of Cartesian coordinate, which Carl has first written down. But that is exercise you can do. We will not go into much about it. So as it is stationary. So we have a time-like killing vector, this zeta mu, let us say, which is equal to delta I, and this is actually symmetric. That means it's symmetric around phi. So we have eta nu, another killing vector eta nu, which is del phi. And if I plot this, this is the r equal to 0. I will come. What is this? Is the a which we have defined. This is the a, and this line is r equal to 0. Then r equal to 0 is not a point. Remember that r equal to 0 is a line. Okay, and if I plot the r equal to constant surfaces, this gives me this type of surfaces. Okay, concentric surfaces for different value of r. And then this surfaces are theta equal to constant surfaces. Okay, this is another interesting thing. And also the zeta mu, which is the killing vector of the time-like killing vector, is not orthogonal to t equal to constant hypersurface. So metric is stationary but not static. This is from the you know that if zeta mu is orthogonal to t equal to constant hypersurface, we have a stationary and both stationary and static metric. Remember. this thing, the metric will blow up at delta equal to 0. It will also blow up at rho square equal to 0. So now we are in a bit of mess. Okay, so the singularity appears both at delta equal to 0 and rho equal to 0. Okay, and we'll see what type of singularities are this. Okay, let's first observe this delta equal to 0 singularity. Similar to the Reisner metric, we can have three cases. Okay, we can so you can put this delta equal to 0 here, and again see we can have three, because this is a quadratic equation in R. We have three cases for the solution of R for delta equal to 0. But the solution for m square less than a square will again give me the naked singularity, which is sometimes considered unphysical, so we will not talk about that. The condition m square equal to a square will give me a non-trivial thing, which is not, once we examine m square greater than a square, and the condition m square equal to a square is the extremal case of that. So we can get everything if I consider this m square greater than a square case. Okay, so for this case, delta equal to 0, delta should be equal to 0 at two radiuses or surfaces. Okay, r plus minus, which is again given by the known that instead of q square we have a square here. So m equal to plus minus root of m square plus a square. So again, plus minus is a null surfaces, so they are the event horizon. Okay, remember they are the event horizon, r plus minus. Okay, beside this curve solution, Einstein event horizon, this is an interesting one. Okay, event horizon is always interesting because they are the sign changes of the radial and the temporal part of the metric. Remember, so this is an interesting surface. So apart from this, there is many additional surface of interest. Okay, so let us check that. So what we can do is we can check for r equal to means for the time-like killing vector. We can do that for the time-like killing vector and see what are the interesting surfaces that we get. Okay, so calculate this norm of the time-like killing vector zeta mu, which is nothing but equal to minus 1 over rho square delta minus a square sin square theta. So see, this doesn't vanish at r equal to r plus, where delta equal to 0, right? This doesn't vanish at there. So there we have zeta mu at r equal to r plus, we have zeta mu equal to a square by rho square sin square theta, which is a square quantity. So this is always positive, which is always greater than equal to 0. Okay, because the time-like killing vector in Schwarzschild solution are null at event horizon and space-like inside. Okay, this is the thing that we remember from the Schwarzschild solution. However, here it is space-like on the r plus, right? This is positive, so this time-like killing vector is space-like at r plus, except for the north pole and south pole where it is null, because theta will be 0 there. Okay, it is null. So let's find the locus of this time-like norm of the time-like killing vector. This is given name as killing horizon. This locus of the point zeta mu equal to 0, and if I solve that, I get this to be r minus m whole square equal to m square minus a square cos square theta. So we have two solutions, both for r plus and r minus. And if I put that r plus, well, the outer horizon is given by this r plus minus n whole square equal to m square minus a square. Okay, so this is an killing horizon. Okay, this is, and we have r plus. Okay, there are two surfaces. Okay, and the region between these two surfaces, this killing horizon, it is also at 2 square. Let us take that r, the positive one. Let us name this as s plus. The killing horizon, the outermost killing horizon, s plus, and the region between these two surfaces, this event horizon and the killing horizon, is known as the ergosphere. No, that is the interesting thing. Inside the ergosphere, you may move in the direction of a rotation of a black hole. Okay, you must move inside the atmosphere. You must move in the direction of the rotation of the phi direction. You can still move towards or away from the event horizon. So in the asteroid, you must move in the direction of the rotation of the black hole. So that is an interesting thing. We will come to that a bit later. However, what about curvature singularity? We have got this two type of horizons and singularities. Okay, coordinate singularities. However, what about the curvature singularity? Remember, curvature singularity will happen at not at r equal to 0. You can find out this curvature invariant scalar, and if you calculate that, it doesn't blows up at r equal to 0, but it blows up at rho equal to 0. And remember, rho square is nothing but aspect plus a square cos square theta, so square, which has a positive quantity. So this can only vanish, okay, at r equal to 0 and theta equal to pi by 2. Wow, what is this? What we have got into? So it's not valid at r equal to 0, not vanishes at r equal to 0, but also at theta equal to pi by 2. What? So remember, r equal to 0 is not a point. Okay, it is a disk. Okay, and theta equal to pi by 2 is ring radius at the equatorial plane. It is the ring which is covering this disk r equal to 0 point, which is not a point but a disk, and r equal to 0 and theta equal to pi by 2 is the ring which is the equation of a ring. So this is also known as ring singularity. Okay, so now let us plot all the different horizons singularities we have encountered with. Okay, so this is the ring singularity, this zigzag surface. Okay, this is a ring, right? This is not a point. Okay, this is the ring that we're talking about. So this inside, this is the inside this thing is the, and this outside are the killing horizon. Okay, and the event horizon, which is given by r plus and r minus, this is the region between the these are the two surfaces of event horizon. Okay, so we have many interesting things here. One is that it is not a point, the singularity is a ring singularity. There are not only event horizon but also killing horizons where the time like killing vector goes to 0. And this shaded region is the ergosphere, where we have to always move in the direction of the rotation of the black hole. And this is the symmetry axis, okay, theta equal to 0. So we can get many interesting things from the rotation of black holes. I am going to discuss a few of that. So what is the angular velocity of the black hole? Okay, let us first think about the angular velocity. So let us say that a photon is emitted in the phi direction. Okay, if we do it like this, a photon is emitted in the phi direction at some radius r, okay, in the equatorial plane. So theta is fixed in the equatorial plane, emitted in the phi direction at some radius. So in the null condition, this is the photon, so null condition will be b square equal to 0, and we will have this terms, okay, gtt, gt phi, okay, and g phi phi, okay, because r is fixed and theta is also fixed. Okay, if I do that, then I will have two solutions for d phi by dt. Okay, so we have two solutions for d phi by dt. Okay, this is related with the how the phi changes. This gives how phi changes with time. Okay, so remember that at the killing horizon, and this equation given by that it has phi t phi and tt coefficients of the metric. But remember, at killing horizon, let us see what this d phi by dt at the killing horizon. Okay, and at the killing horizon of the curve metric, we have gtt equal to 0. That is defined by, that is how the killing horizon is defined. So if I put gtt equal to 0, I have two solutions. One is d phi by dt, either it is equal to 0 or it is equal to, if I put all these things back here, it will give me twice a of 2m whole square plus a square. So these are the two solutions. Let us first see what this solution is. So d phi by dt is proportional to a, or in the direction of a. So photon moving around the hole in the same direction of the black hole. So photon will move around the black hole and in the same direction of the black hole. It cannot go in the other direction. Or d phi by dt can 0. So if a photon is directed against the black hole, spin, it doesn't move at all. So it cannot, even if it is directed against the black hole, it cannot move. Okay, So this phenomena where the photon has even everything has to move along the direction of the black hole is called the dragging of the initial frames. Okay, in every rotating black holes or rotating black holes there has to be some inertial dragging. Okay, this is a totally general relativistic effect. Okay, there is no Newtonian counterpart of this effect. Okay, and many of the experiments have done to prove that dragging of the inertial frames, and then for black holes these are very huge. Okay, so massive particles are dragged along the black holes, not inside the killing horizon. Uh, uh, Black hole rotation inside the killing horizon. So massive particles are dragged along the black hole's rotation inside the killing horizon continues, and it continues till approaches R plus. Okay, inside the killing horizon. So killing horizon is inside here. The massive particles are dragged until it continues that drag till here R plus. Okay, and once it reaches R plus, let us see what happens. So at R plus, we define the angular velocity of the black hole. The drag which is at the R plus boundary, the event horizon at R plus, and that is given by omega h, which is the spin of the angular velocity of the black hole. It is given by d phi by dt at R, which is nothing but a by R plus plus a square. Okay, you can check that. You can just put it there and check that. This is the how the angular velocity of a black hole is defined. Okay, which is defined at the point of the event horizon R plus. So we can also have geodesic motion. Okay, let us only consider for massive particles. Okay, what happens for the geodesic motion? So if I can write the force momentum, which is mr dx mu by dA tau. Okay, this is the force velocity, and mr is the rest mass. So remember, this mr is the rest mass, and m was the gravitational mass of the black hole. This is the rest mass of the particle. Okay, so we have two killing vectors. So we have, for rotating black holes, we have two killing vectors. So two conserved quantities. One is the total energy, which is given by zeta mu p mu, where zeta mu is the killing vector. Okay, associated with this energy, which is the this is the time lag killing vector. Okay, and if I put it back here, I will get this equation. The energy of the black hole to be this. Okay, so this is negative put here. I will discuss why negative the equation is in terms of negative quantity, but this is not negative, this is positive. I will discuss. And the another quantity, which is the total angular momentum L, okay, which is nothing but this axial killing vector eta mu p mu, and this is given by this equation. Okay, you can check that. This is not much mathematics about, no physics about it. This is just some algebra you have to do, sit down and do. So please do that. So inside the ergosphere, zeta mu is space-like, right? You always know, because it flips signs. So this has to be, in the energy has to be less than 0. However, at infinity, both this eta mu and p mu are time-like. So they end up, and the inner product is, therefore the inner product is, this has to be negative. Okay, so there is a negative sign sitting in beside that to make the whole energy to be positive. Okay, all particles outside the killing horizon must have positive energies. Okay, particle inside positive energies, and particle inside the killing horizon must have negative energy and remain on a geodesic inside the killing horizon, or accelerated to positive energies and come out to escape. Okay, so inside the particle outside, this energy should be positive. Inside the particle, energy is negative, and if a particle comes out, then it's again positive, energy has to be positive. So there is a way of, it gives us the hint that there is a way of extracting energy from a black hole, and this is given by this pendulous process. So we will discuss it more here in more detail. It is nothing but a simple idea. Okay, so what we do is you arm yourself with a large rock, right, and lead towards the black hole. So let us find what is the initial energy, E0, which is nothing but this killing vector times the force momentum. Let us the force momentum here P0 mu, let us have, and this is positive. Okay, initially this is positive because we are not inside the ergosphere. However, once inside the ergosphere, once we go inside the ergosphere, because we have left into it, once we go into the ergosphere, we throw the rock in a specific way. We have the specific I will define. I will show you a picture in what specific way we have to throw the rock. And is in a specific way, and now we are detached. This was the momentum, energy, force momentum with me and the rock, and now when I have thrown it, my force momentum is, this is my force momentum p1 mu, and the rock momentum is p2 mu. And from the conservation of momentum, we have this condition: the instant I have thrown the rock. Okay, so now I can contract this equation with the Killing vector zeta mu, and I will get E0 equal to E1 plus E2. So you can throw the rock such that this E2 is less than 0, right? I have to tell that because I can throw it inside the atmosphere, and energy can be negative. Okay, once I do that, since energy is conserved, if I come out my energy, this E1, this is negative, so this has to be greater than E0, right? This has to be so E1 equal to E0 minus E2, but E2 is negative, so E1 is equal to E0 plus E2, and both are positive. So this E1 is equal greater than E0 here. So you have more energy that you have entered. So once you have come out of the black hole, you have more energy. Okay, where the energy comes from, right? Energy is not even, you cannot generate energy. I have extracted energy from the black hole, right? I cannot generate energy. So this is the process. This process is known as Penrose process. Extracting energy from a black hole by decreasing its angular momentum. How the energy is extracted from black hole? Energy is extracted from black hole when its angular momentum decreases. So the main trick here is you have to throw the rock against the black hole rotation for the trick to work. Okay. So let us say that this is the figure which shows how to throw the rock and how can we extract energy. This is the top view. Okay, this is the ergosphere. Okay, remember what is this? This is the Killing horizon, and this is the event horizon. So what we can do, we can, with this initial momentum, with me and my rock, I can jump into the black hole. So once I have gone inside, I can throw the rock in a particular way, right? P2. Now P2 becomes, because I know I can throw, because I have seen that this can be done, energy can be negative, and if I throw it in a particular way, then the energy can be negative. I have to throw that in the particular way inside the black hole. Okay, right? I have to throw it in the particular way so that this energy becomes negative, which when contracted with the Killing vector, and then if I come back out of this, I have this momentum, and now the energy corresponding to the momentum is greater than what I have entered into it. However, this throw, the way I have thrown it is such that this angular momentum of the black hole has been reduced. So that reduction in angular momentum is shown by this increase in energy of mine. So this is how the extraction of energy from a black hole is done. Okay, and this is an interesting formula and process which was first shown. There is also much more mathematics included with it. You can do that. However, this is a simple way of thinking this thing. Okay.